Welcome everybody. My name is Parvinder Jhita and I look after Bentley's SACS product. Today's tech talk will cover the offshore wind turbine platform design capabilities included in SACS. And let's get going on that. Give me a second. SACS has what I would call full life cycle applications for the design of offshore wind turbine platforms, starting from fabrication, installation, to in-place conditions, and also decommissioning. Today's tech talk will focus on the in-place design of these structures. Okay, first let's define the problem. A typical wind turbine is subject to three sources of loading, and this includes the wind load on the turbine, the wind load on the structure, and the wave load on the structure. In SACS itself, the wind load can be represented in terms of either a wind spectrum or by a wind velocity time history. Alternatively, there's a third option where you can apply discrete nodal time history loads also. The wind spectrums include basically the one common API spectrum, the Harris and the Camel spectrum. Now, the differences here are the API and the Camel are height dependent, whereas the one common and Harris are not. Alternatively, like I said, you can also supply, if you have a recording of the wind velocity time history, you could use that directly to generate the load on the structure. Looking at the wave loads, sorry, I got the title wrong there. And in this case, again, we can represent the wave load either as a wave spectrum or a time history of the surface profile. And in this case, the various wave spectrum that are available include the Pearson-Moiscovich, John Swap, Ochi-Hubble, and user-defined. In addition, if you have the measured wave surface profile of that location, you could use that directly to generate the actual loads on the structure. Looking at wave forces in large tubular columns such as monopiles, in SACS we use the Morrison's equation to actually generate the wave load. And as you all know, the Morrison's equation is only valid for provided the diameter of your tubular is less than 1/5 of the actual wavelength. In this case, in SACS, we actually employ the McCamey and Fuchs approach, where they've actually calibrated the mass coefficient used in the Morrison's equation with the actual diffraction panel results. Okay, so this next graph actually shows a comparison between the two approaches. Here at the top you see the pure Morrison's equation, and basically the result in red is the McCamey and Fuchs approach applied to the coefficient of mass. And basically what we're doing here is we're increasing the diameter of this tubular column and measuring the base shear. As you see, for low diameters, the two approaches give the same results as you would expect. The wind load on the actual turbine itself causes a rotation of the turbine, which in turn will generate your aerodynamic and mechanical loads on top of the tower. And these can be represented directly as a force time history load. So provided we have the three sources of loading, the turbine mechanical and the aerodynamic force, wind spectrum, wind velocity, wave spectrum, or the wave surface profile, we can go ahead and do a full fatigue or a strength analysis of one of these structures. Now in SACS we have various options available, and the first one is what we call the SACS wind turbine process. This is an uncoupled process. And then we also have the SACS interface to the fast aeroelastic program, and also have an interface to the GH bladed aeroelastic program as well. And currently, we've just recently developed a dynamic superelement to communicate with Siemens B-Hawk aeroelastic program. Okay, so first let's look at the actual uncoupled wind turbine process. And the reason it's uncoupled here is the actual turbine loads are supplied to you by a third party. And in this case, you would be modeling the actual jacket, the tower in SACS itself. The wave and wind loads will be generated in SACS, and like I sort of said, the turbine time history loads will be supplied to you by a third party, typically the turbine manufacturer. And then once you have all these, then you can do the full analysis and the post-processing in SACS. That includes fatigue, member checks, and joint design. This essentially is an iterative process because it's uncoupled and may require about 3 iterations before the turbine manufacturer and the actual designer of the foundation agree on the results. The way this process works in SACS is that we've simplified it to minimize any user, errors creeping into this process, because you're dealing with thousands and thousands of simulations. And basically, to run fatigue analysis, you would be supplying 2 files. First is a control file, and secondly, a partial fatigue input file. The control file basically defines the location of all your simulation input files, which is in other words, the directory structure. And the partial fatigue input file contains items such as the design life, fatigue design life, if you have any factors of safety, the SCFs, the ascent curves that you want to use, and any overrides that you might have for your fatigue analysis. This little video here shows you exactly how simple it is to actually run one of these analyses. And basically, you would go to the utilities area in the SACS executive, and we'll supply the control file, which is a SACS-in file, and then also the partial fatigue input file. In this case, we are looking at 20 simulations. And as soon as you give those input those files, we'll spawn off a multi-core process. And I think we're using 8 cores in this simulation. So once the analysis has gone through all the simulations, what we'll do is we'll actually accumulate all the fatigue results and then give you the fatigue life of the structure. Okay, so right at the bottom, there should be a fatigue file, and then basically you can look at the total damage. Here you'll see some fatigue damage results. Okay, I'll move on. Okay, the strength analysis is the uncoupled analysis. This works slightly differently. In other words, basically you're dealing with thousands and thousands of simulations. Each simulation could have 12,000 load cases. So essentially you will end up with maybe, up to 60 or 80 million easily load cases that you want to look at, and then even more unity checks. So basically you got to look at millions of unity checks, and you've got to figure out which are the critical ones. And in this case, what you would input is a control file, very similar to what I showed earlier, a partial C-state input file. This will contain your dead loads, any gravity loads that you haven't modeled, because you've got to combine these with your dynamic loads once you've done the dynamic analysis before you do a code check. You can also include your nonlinear foundation and a joint can input file to design your tubular joints. In the previous fatigue analysis, I forgot to mention that you can also do a fatigue analysis of the pile foundation itself by generating a pile solution file. So for a strength analysis, we'll input all these files, we'll do a multi-core analysis, and then we'll pass on the millions and millions of unity checks into a database. The database is then screened, filtered for the critical unity checks, and we'll supply the information such as the load case in that particular simulation, which simulation, and which portion of the code that's been exceeded. And so once you have this, then you can go ahead and do a full interactive redesign of the structure using the SACS post-view program. Here again is a little animation showing you how to do a strength analysis. Again, you have the options here to set the upper limit for the unity checks, as well as providing the various files that it needs. Again, once the analysis is complete, all the unity checks, like I said, are passed into a SQLite database, and then this database is then filtered, and we supply you the critical unity checks, basically. Okay, so moving on a little bit, to generate the load cases to design for an extreme wave, you have a couple of options. Either the first option is to run a multi-seed analysis, usually up to 6 seeds are recommended, and then average out the actual internal loads to give you the critical unity checks corresponding to these. Now, the alternative, a quicker way of doing this is to, how do you say it, embed a constrained wave in your irregular wave. In other words, this is an H max wave, and then you could use this directly to do your extreme wave analysis. Next, looking at the SACS fast option. Here again, what we've done is we have a fully coupled analysis, and in this case what we've done is we've combined the actual fast code with the actual SACS wave response code. These are two combined and compiled together, and then in this case we can actually model the actual structure in SACS. The turbine is modeled in fast, and then we do a fully coupled time history using the wave wind loads that are generated by SACS, and this like a sort of coupled with the turbine forces from fast. And once you've done this, you can go ahead and do the post-processing in fast itself. Again, this is a little demo showing how easy it is to go ahead and do this. Again, under the utilities menu here, you have an option to generate a fast common solution file or do a SACS fast analysis. Click on the start wizard, and then you end up supplying all the necessary files, which includes the SACS input files, wave response input files, as well as the fast input files in this case. And again, once you've done this, and basically what we do is we'll generate a common solution file. It's actually an OCI file which will contain initially all your input load conditions or your load conditions generated at each time step. And then once you have this, then you can go ahead and do a full analysis and generate a common solution file for your fatigue analysis or your strength analysis. Again, this is the black window here is basically fast running in conjunction with SACS. And it actually goes fairly quickly. So you can say fast is fairly fast. Okay, so moving on to the SACS GH bladed interface. In this case, we have an option. We have a front end to GH bladed where you can actually go ahead and model the actual structure in SACS, and then this can be passed on to GH bladed. Now, obviously, there are certain attributes that exist in SACS that don't exist in GH bladed, so you might have to do some minor modifications in the GH bladed program, so your model is actually acceptable to that product. So once you've got your model into GH bladed, then you do a fully coupled time history analysis in the GH bladed product. GH bladed, as everybody knows, can do a full hydrodynamic analysis of an offshore wind turbine structure, including nonlinear foundations. So once the analysis is complete, what we do is we pass the results from GH bladed into SACS for the post-processing. And so basically we have a front end and a back end to this product, where we do the backend includes a fatigue analysis, member checks, and the joint design. Now, GH-Bladed actually generates a control file for SACS. So the product will generate a SACS.in file. And again, this file will contain the model information, and right at the end of the actual file, it'll contain the number of simulations. In this case, we have 6, and then the location of the various simulation results, and including the probability of occurrence and the actual design life given in seconds. So this is generated by GH-Bladed, and SACS will actually use this to automate the post-processing. And again, the process is very similar to what I showed you for the uncoupled process. In this case, the user will supply that SACS in file that's generated by GH-Bladed, a partial fatigue input file described below, and the GH-Bladed results. SACS will then conduct a multi-core analysis, a post-processing analysis, and then output the fatigue results in this case. And similarly for a strength analysis, you have the choice. Again, you can put in a control file, a post input file that the post input file describes the type of code checks that you want to conduct, a joint can input file to design your joints, and the GH-Bladed results. And again, you will do the multi-core analysis in SACS. And again, you will have thousands, or actually millions, of unity checks, which are then passed or stored into a database, which is then filtered, and then will give you the critical unity checks. All very simple to run, as I showed the uncoupled process earlier on. We have a slight variation to this analysis in that the results coming out of GH-Bladed only have a single load factor. Now, the codes require a different factor to be actually applied to the dead loads, and a different factor to be applied to the dynamic loads. So what we've done in SACS is we use the actual combine module to separate the dynamic and gravitational components, and then apply the various load factors, and then recombine the results, and then later on, following that, you'll do your strength analysis. Looking at our link with Siemens BHawk, this is actually basically the dynamic superelement. This was released with the SACS 10.0. It's a new module that's been added to the SACS suite of programs, and in this case, it's a 3-step process. The first step is to actually do a modal analysis to generate a mass file and a mode file, and in addition to that, you're generating a dynamic superelement data file and a dynamic superelement transformation file. These are later used to generate either a load vector, and also to actually to generate the actual dynamic superelement. If you want to generate a load vector, this is optional. Then you would need to run wave response, and this will basically use the mass and mode files and the transformation files used in the previous step. Running wave response will generate a dynamic superelement force file, and finally the third step is to use the dynamic superelement input file, which describes the type of damping you require, etc., and also the data file and the force file. And then after the dynamic superelement has been run, then you would actually get the reduced stiffness matrix mass and a damping matrix, and also a reduced load vector. And again, these could be used directly now by the Siemens BHawk program. Looking at the various, the options for parallel processing, in addition to being able to parallel process on your local PC, what we're also in the process of offering, and this will come out very shortly, is cloud computing. And basically, this will give you the option to access thousands of nodes for parallel processing on the cloud itself. There is a drawback to this, and that's the upload and the download time. For large files, it could be very slow. So in the case of uncoupled process, this is fantastic. For a GH-bladed result analysis, if you're doing that on your computer and uploading and downloading those, well, actually uploading the result files from GH-bladed, this may not work unless you actually run GH-bladed on the cloud itself. Okay, so we did a quick simulation here. Basically, we used one simulation, and if we found that that took around about an hour, then we'd use 500 simulations with 500 nodes. And in both cases, each simulation contained 12,000 loads. And for the 500 simulations, it only took 1 hour 15 minutes. So a slight increase in runtime, but a great saving in the overall actual analysis time for the whole design. The link to GH bladed also gives us a link to the GH Tidal bladed interface. So if you're actually interested in designing marine turbines, again, you have this capability through the GH bladed product. And in this case, we're showing some underwater marine turbines. I won't go through the whole animation because I don't want to spend too much time on this. Okay, so to give you a taste of who our clients are out there, this is a brief list of all our clients, and not all of them directly, and then also give you a brief list of the actual projects where SACS has been used. This is the London Wind Array Wind Farm, and these are the slides presented by COE. And basically 175 steel monopile foundations, water depth up to 25, penetration up to 40 meters below the mud line. And basically they say they use SACS program for their calculations. This is the Godian United Power Technology letting wind farm in China. This wind farm will basically is expected to include 4,400 megawatts, starting with 300 megawatts during the first phase. And again, they use SACS to analyze and design this structure. And this is the first for SACS in that this is the Block Island wind farm. It's the first offshore wind farm in the US. And we're proud to say that it was actually designed using the SACS wind turbine application. Again, this was 5 51-meter tall foundations in a water depth of about 28 meters, and you're talking about a 6 megawatt Alstom turbine on these structures. And again, this actually used the GH bladed interface. This is the Wikinger wind farm off the coast of Germany in the Baltic Sea. 70 platforms in this case, and water depths ranging from 37 meters to 43 meters. And again, like as I've said, there's 70 platforms which are being installed right now. And basically that brings me to the end of this tech talk. So if you have any questions, we could definitely field those now.
Okay, I have a few questions coming in, and I'm going to give these to you, Parvinder. What kind of wind turbines do you support?
When you say what type, do you mean offshore or onshore? We can do both, basically. The actual wind turbines, the manufacturers. With those people using GH bladed, that's not an issue. I mean, we have a large number of companies in Southeast Asia that use the GH bladed product. Siemens, like I just showed you, that we have a direct link with them with the actual what you call it, the dynamic super element, and then anybody using fast, we also have a link to them. And in my view, going forward, I think it's the dynamic super element is probably the best route. It's the easiest route link to other products. So, and the super element generated by SACS is purely general. In other words, we are not, how do you say it? We don't define the format in one sort of, we don't have a single format. The format is adjustable to meet other products. So in essence, Jeff, I assume that we can handle quite a few of those if they have the capability to import a SACS dynamic super element.
Mm-hmm. Okay, let's see. We have a question. Are there sample files available to see, looks like, how they look and interact in SACS? I guess basically, do we have any sample files for the various types of wind turbine analyses?
Absolutely, we do. Obviously, the GH bladed files are rather large because you're talking about results, and to actually email or FTP those, all of those would take a long time. So we normally just, yes, but the answer to your question is yes, we do have sample files.
Now, just as a follow-up, are those available when you download SACS, or do you have to contact Bentley directly to get those?
You have to contact us. Like I sort of said, those are large files in some cases. So you would actually contact us and we'll supply those files to you.
Okay. Here's one. We may not know this, but I'll go ahead and ask you, Parvinder. What is the max water depth that you have ever designed? And I'm assuming this is for wind turbines.
Yeah, I do believe, I think it's to 680 meters that you can design an offshore wind fixed platform, and going anything above 80 meters is usually they're looking into floaters. So that range is there. I think it's 40 to 80 meters is the fix. Below that is a monopile. And then afterwards, you'd have to start looking at floating structures. And basically, again, I'd say here again that Bentley also acquired the Moses product. And the Moses product is same as what SACS is for fixed product, platforms. Moses is the same in the oil and gas industry for floaters. And so what we are currently doing is linking the two products to give you the ability to actually be able to design floating wind turbine platforms also.
Okay. Let's see. We have one more question here. Can you clarify the development of unity checks relative to allowable stress design versus LRFD design?
Can I
I don't know if this is related to wind turbine or if this is just more of a general question.
Right. I mean, I don't understand what the question is, but I'll say that we have both. Either if you're doing LRFD checks or working stress design, we have both options. And the safety factors I mentioned earlier on were basically for the load factors or for the LRFD code check, which is essentially what's required in Europe. And also, I think it's becoming the actual design code here in the US as well. It's basically based upon the ISO code.
Right. Okay. Here's one. Is the wind product separate from SACS? So can you just get a wind turbine analysis program in SACS?
The wind turbine license actually uses a lot of the how do you say, the main modules, the best modules in SACS. So it contains the enterprise, the PSI capabilities, the fatigue enterprise. So all those are bundled into the wind turbine license. On top of that, you're getting all the automation and also all the specialized interfaces that we have with the various aeroelastic programs. So yes, you would actually purchase the wind turbine license to get these capabilities. is part of SACS.
And there was also a follow-up question, and I can answer this. What is the extra cost? If you're interested in purchasing the wind turbine license, you can contact your account manager at Bentley and talk to them directly about that. Okay, here's another question. Is the database for the results the normal PostView database?
It's a different results database right now. It's not for the PostView database. It will become a unified database later on, but currently the two are separate.
And that's a SQLite format?
Correct.
So if you're familiar with SQLite, there's a lot of ways that you can manipulate that information to get the results that you're interested in. In fact, I made a presentation that will be uploaded shortly that talks a little bit about working with report databases. It'll be available on the Learn server, and I can provide a link in the chat for that. On the same subject, is this presentation available as a download?
Right now, no. I think Natalie could tell you about that. I think we will be making it available. She'll talk about it at the end. She will address that later. Yes, it will be available.
Yeah, I just posted a link to this special interest group learning path.
Okay.
Is there any support for European standards used for code checking?
Absolutely.
Yeah, we have. Okay, he expanded that question to ISO, NORSOC, Eurocode, Danish standard, German and UK codes.
All of those codes are included. When you come to the German codes, basically we have the German annex to the Eurocode.
Right, those are ISO and Euro codes that have annexes.
Yes.